So let's take a look at cross-sectional volume. So for problem number 1, we have to find the volume of the solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1, whose cross-sections are squares perpendicular to the x-axis. Now the formula for the cross-sectional volume, if the cross-sections are perpendicular to the x-axis, is going to be the integral from a to b of a of x dx. And a of x is basically just the area function of the cross-section. And if it's for the y-axis, if the cross-sections are perpendicular to the y-axis, then we have the integral from a to b of a of y. So all we need to do is put everything in terms of y, if they're perpendicular to the y-axis, and x if they're perpendicular to the x-axis. Now looking at the graphs bounded by y equals x squared minus 1 and y equals x plus 1, the problem is trying to tell you that this shaded region is going to be the base of the solid, and that each cross-section perpendicular to the x-axis, so like here, 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 they're all going to be squares. So let's take a look at this from another perspective. So we're kind of looking at it from a side view, where this is the region of the base that's supposed to be shaded, and we have the x and y axis. So we're supposed to take each cross-section perpendicular to the x-axis, so we'll have that like this, and each cross-section is supposed to be a square. It's going to look something like this, where they're upright. And each cross-section, or the base of the square, is going to be called S. So recall that the area of a square is just going to be base times height, or in this case, it's going to be just S times S. So area will equal S squared. Now, looking back at the formula, we know the volume of a known cross-section is going to be the integral from a to b of the area function. And we know that the area is equal to S squared. So the volume is just going to be the integral from a to b of S squared. So S, as we can see right here, is simply just going to be the area between the two curves. And to find the area between the two curves, using x bounds, we can just do top curve minus the bottom curve. So the top curve, so S is going to be the top curve, which is x plus 1, minus the bottom curve, which is x squared minus 1. So I can distribute out that minus, so I get x plus 1 minus x squared plus 1. So then we get x minus x squared. We get 1 plus 1, which is 2, plus 2. So now what I can do is take this and plug it in for S. So if I were to scroll down a little bit, we get the integral from a to b of x minus x squared plus 2 squared dx. And the very last thing we need to do is find our bounds from a to b. And since we're doing it perpendicular to the x-axis, since the cross-sections are perpendicular to the x-axis, we need to be using x bounds. So in order to find the x bounds, we can just find where these two curves intersect. And those points are here and here. So in order to find where they intersect, we can just set them equal to each other. So we can say x squared minus 1 is equal to x plus 1. I can bring them all to the same side. So subtract over the x and the 1, so I get x squared minus x. Negative 1 minus 1 is negative 2 equals 0. This is a quadratic equation, so I can factor it out. So I need something to multiply to get me negative 2, to add to get me negative 1. And that is x plus 1 and x minus 2. So the x points of intersection, or the x values of intersection, are at x equals -1 and at x equals 2. So now I can take these values and plug them into my formula, or my integral. If I were to, so we're going from -1 to 2. So I can rewrite this as the volume of the cross-sectional volume equals the integral from -1 to 2 of x minus x squared plus 2 squared dx. Now you would most likely want to use a calculator to evaluate this integral, but this is the final answer. So now for number 2, the problem asks to find the volume for the base of a solid bounded by y equals x cubed, y equals 0, and x equals 1, whose cross-sections perpendicular to the y-axis are semicircles. So notice how it says y-axis. So now we need to put everything in terms of y. So looking at the graph of y equals x cubed, y equals 0, and x equals 1, the area being bounded by those graphs is this small region right here, and that is going to act as the base of the solid. So if I were to zoom in, make it a little bit bigger, it kind of looks like a right triangle, almost. So now the problem's asking that, or the problem's saying that each cross-section perpendicular to the y-axis, so if this is the y-axis here, each cross-section perpendicular to the y-axis is going to be a semicircle, so kind of like this. And so we're going to name this the base of the semicircle. We're going to name that S, the cross-sectional base. So in order to find the area of a semicircle, the area is going to be equal to pi r squared over 2, or half pi r squared. And so in order to do this, we need to put S in terms of r. So the radius is actually going to be halfway. So if S is the entire base, the radius is actually just going to be halfway. So 2r, or 2 times r, is going to equal S. So now what we need to do is isolate r, so that we can substitute into the area equation. So r, obviously we divide by 2, so r is going to equal S over 2. So now what we can do is take this and sub it in for r. So then area will equal, I'm going to actually bring out the 1/2, so I say 1/2 pi times r, which is equal to S over 2 squared. So S over 2 squared is the same thing as S squared over 2 squared, which is 4. So then the area will equal 1/2 times pi times S squared over 4. So I can multiply 2 and 4, so I get pi over 8 times S squared as my area. So now that we have the area, we can set up our integral. So the volume is going to equal to the integral of a to b of pi over 8 times S squared. So to simplify the equation a little bit, I can actually bring out the pi over 8, since pi over 8 is a constant, times the integral of a to b of S squared. So now we can find our two bounds, a and b. So since we're going perpendicular to the y-axis, everything needs to be in terms of y. So in order to find the y bounds, we can first change our two equations so that they're in terms of y. So x is already in terms of y, so x equals 1 is one of the equations, and we need to change y equals x cubed. So in order to get rid of the cubed, we can just cube root it. So the cube root of y is going to be equal to x. Now to find those points, we can just find where they intersect. So we can say that 1 is equal to the cube root of y. In order to get rid of that cube, we can just cube root. In order to get rid of the cube root, we can just cube both sides. So y is going to be equal to 1 cubed which is just simply 1. And that is the point of intersection. And notice that we're going from the y value of 0 all the way to this intersection point, which is 1. So if I change my integral here, pi over 8 times the integral from 0 to 1 of s squared. Now all that's left to do is find the s. And s is going to be equal to the right curve minus the left curve, since this is in terms of y. And I apologize, I forgot to put, instead of putting dx, I should have put dy for all of these, because everything we're doing is in terms of y, so got that. So since s is the cross-sectional length of the base, we just need to do right curve minus left curve. So the right curve is going to be equal to x equals 1, and the left curve right here is going to be the y, or x equals the cube root of y. So s is going to be equal to right curve minus left curve, obviously. So 1 minus the cube root of y. So now what I can do is substitute that in for s, and our final answer for volume is going to be pi over 8 times the integral from 0 to 1 of 1 minus the cube root of y squared times dy.